In our last lecture, we finished off and closed out the system of fluid equations by assuming a barotropic equation of state. That is, an equation of state where the pressure is only a function of the density. And that works for us quite well in many situations, but in many astrophysical situations, we can't assume a barotropic equation of state. And so then, in order to solve our system of equations for fluid dynamics, we need to have one more equation. And for that, we're going to bring about the energy equation. So the energy equation is going to start out with the first law of thermodynamics. And hopefully, the first law of thermodynamics is relatively familiar to you. So the first law of thermodynamics tells us that for an amount of heat absorbed by a fluid, dq, so we allow some amount of heat, dq, to be absorbed, and that is equal to the change in the internal energy of the system plus the change in work, which is just the pressure times the change in volume of our fluid element. So just make that clear. This is the internal energy. And this one is the work. So we can write this in a Lagrangian sense, where we can say that remember, capital D means it's a Lagrangian partial derivative. So we're going to write, and this would probably be better written as E like that. We're going to write that the change in energy with respect to time is equal just simply to the change in the work with respect to time plus the change in the heat with respect to time. And this dq dt is the energy in a fluid element. So we're considering, because this is a Lagrangian fluid, we're considering each element individually. This is the energy gained from the surroundings in that particular fluid element. And we can go a little bit further and write that, of course, because we said that the work was just P dV, that the change in work with respect to time must be equal to, in fact, this is a negative, but it's a similar idea of the volume with respect to time. And that's equal to pressure over the density squared, change in pressure, over change in time. And we can also say that the change in energy with respect to time is just the pressure over the density squared, d rho dt, minus some q dot, which I'm going to call q dot cool. So that's just replacing my dq dt by saying I've got an amount of energy gained from the surroundings, and I'm going to call it a cooling function. So q cool is a cooling function. And I write it that way because in astrophysics, it's often easy to identify a cooling function. So what happens and how much energy is lost or gained through some astrophysical process, and we determine it in terms of a cooling function. So it's a cooling function, and that's positive if the medium has cooled. And clearly, it's negative if the opposite is true, and that the medium has increased, has warmed. Okay, so from there, we want to let the total energy of the system, so this is total energy of the system, is equal to the density of the system plus 1/2 u squared. That's obviously the kinetic energy term. Then we have a potential energy term, and we have an internal energy term. And that allows us to come around to the point of saying that the change in energy with respect to time is equal to the total energy over the density times the density, the change in density with time, plus rho u plus du dt plus d psi dt plus p over rho squared d rho dt minus q dot cool. All of that is times rho. So that comes from substituting in my various forms of the equations that I've written above. Now, all of this is considering a Lagrangian element. So we're dealing with a change in that particular fluid element. But in order to fill these in and solve our fluid equations, which we've written out as Eulerian equations, then we need to do the transformation, which takes this energy equation, which is a constant energy set off of the first law of thermodynamics, and we have heating, we have cooling, we have a change in internal energy, we have kinetic energy. All of those things need to be translated from an individual fluid element to considering the fluid as a whole, and as it's moving past some particular position, and that means a transformation from a Lagrangian to an Eulerian. So remember how we do a Lagrangian to an Eulerian transformation. Well, we do that for, let's say, the quantity in this case is the total energy. So the Lagrangian change in time, energy with time, is just related to the partial derivative of energy with respect to time in an Eulerian sense, plus the velocity vector dot grad E. You probably remember that as being how you transfer Lagrangian to Eulerian. And then we're going to need the continuity equation. In order to simplify this whole energy equation, we need the continuity equation. So the continuity equation is, of course, the change in density with respect to time, and I've written this in its Lagrangian form, minus rho dot divergence of velocity, and that's the continuity equation. So we can combine all of these different aspects in our energy equation. And the intention here is to be able to write out a simple energy equation, which we can use that is the conservation of energy. So from there, we move forward to saying that change in energy with respect to time, the Lagrangian, is E over rho dot rho grad U minus U grad P minus rho, and this is just a series of substitutions which you can do yourself. Grad phi plus rho, not phi, I meant psi, sorry. Partial derivative of psi with respect to time plus rho U dot grad psi minus, it's a long equation, but don't worry, it simplifies, times rho divergence of U minus rho times the cooling. So I've just substituted in a number of things and written this, expanded out my equation. And all of that simplifies down to just being the energy, oh, that's P, not rho, times the divergence of the velocity field. So that's how our pressure and our energy are changing with the flow through, minus the velocity field dot with the change in pressure, minus rho Q cool. And of course, substituting in for the Eulerian to our Lagrangian aspect allows us to finally write down that the change in energy with time, an energy conservation equation, plus grad dot E plus P times the velocity field is equal to the density of the medium times the cooling function plus rho times d psi dt. And that is the energy equation. Which means it is an equation of conservation of energy. And now we have, just like we would work with in any sort of Newtonian sense, we have a conservation of energy, we have a conservation of mass, and a conservation of momentum equation. Unfortunately, life is more simple than this equation, because usually d psi dt is equal to 0, which is to say that the potential energy is not changing. The potential is not changing. And so from there, the change in energy with time is a function just of P and rho and the cooling function. And the cooling function from an astrophysical sense is something that we can start to define. We can start to think about, well, how would you get cooling about, and then write out what those may come from. And so cooling can come about from convection, it can come about from radiation, and in fact, radiation is the dominant source of heating and cooling in most astrophysical situations, not all, but most. And it can also come about from conduction. And so we can apply those and think about what they come from. So I'll just finish off